to go.
Super.
Speaker for the first one.
First speaker is going to be a remote talk by Kunyang Lee, who I don't see has joined yet.
And there is a minute or so, maybe we can wait.
Okay.
Otherwise, definitely, yeah. Otherwise, we have the next speaker in the audience, so we can swap.
Great. Okay, I guess we can give the first speaker a fair chance.
You are a minute early by my clock.
I'll sit up anyway.
Sorry, excuse me.
So you tell me. Sorry.
It's like we're in a club or something.
Nate, you have to make the choice. So.
Okay. It looks like everybody else is here. And I think, I don't know. I mean, we can wait 15 minutes if they show up with 5 minutes left, but maybe we can just move on. If they show up, we can maybe squeeze them in at the end if there's time. Okay. Well, thank you everyone for coming again to this wonderful workshop, and good morning to you. I wish I could be there in person, but as you could probably tell, I'm a bit under the weather. And so first we're going to have Stefano Bondani speak for us, and he's in person there, as I see. He's going to talk to us about gravitational waves from primordial black holes orbiting Sagittarius A star with Lisa and Mu Ares. Take it away, Stefano.
Thank you very much. So today, I'm going to give this talk about gravitational waves from primordial black holes orbiting Sagittarius A star with Lisa and Mu Ares. Of course. So, because what I will be talking about revolves around Sagittarius A star, I can still lay first picture that we got of Sagittarius star, and here's a brief outline. So the story goes like this. People have been looking for a dark matter candidate for a long time, and because the results have been inconclusive, maybe some people try to put primordial black holes instead of a generic dark matter component as an answer to this problem. And if they do behave like dark matter, maybe they would follow something like an Navarro-Franken-White density profile or something similar to that when they get when they are part of the dark matter inside galaxies. And maybe if they are, if you look close enough to the center of our galaxy, maybe they should be close enough to Sagittarius star and start orbiting it. And if they do so, maybe they will emit gravitational waves, and maybe we can hope to detect them. So as you can see, many maybes here. Of course, primordial black holes were proposed many years before dark matter was even a problem by Hawking and Zatovich and other guys. And the thing is, if you want to make dark matter with primordial black holes, I will not spend a lot of time on this, but just a few words. You've got two windows where you can make 100% of dark matter. One of them, they would be too big, above 10 to the 14 solar masses to make any physical sense. And one of them would be very small, and that would mean that if to make any considerable amount of dark matter, you would need to have them everywhere. And by now you would have probably noticed. Also, you would have never any chance to detect them with gravitational waves at these small masses. So your next best bet is to look into this small window, which is labeled C, which is corresponding to about 1 solar mass. So maybe that is the way to go. And of course, a more robust test, or a more robust input on this is to look at possible channel formation for primordial black holes that show you that it is most likely that if primordial black holes do actually exist, if they form in the post-inflationary era, by whatever channel they formed, it is most likely that they formed with a 1 solar mass. So it looks like if you want to make a model with primordial black holes in it, a good way to start is to choose 1 solar mass primordial black holes. So many people have been trying to look at this problem by this point of view, of course, before us. And here is just a small example of a few of the papers, well, many of the papers that have looked exactly at this. And one of them, for example, says, searching for primordial black holes with stochastic gravitational wave background in a space-based detector frequency band. So basically what people did was to just see if LISA will be capable, in fact, of seeing a 1 solar mass primordial black hole orbiting Sagittarius star close enough to actually detect it with the sensitivity of LISA. And this is a good enough argument to write something about it. But our question was, will it actually do so? I mean, will we actually have the chance to detect any primordial black holes in there? Do we have we have some hints from observations that maybe we don't have enough primordial black holes there to begin with. So even though LISA is capable of doing it, is another thing to say that it will detect these kind of objects. And so let's make a few first order assumptions. Let's try to think about a simple system with circular orbits of these primordial black holes orbiting Sagittarius star with one only mass, so a monochromatic mass function. And let's assume that they did not accrete during their history, which is a bit of a debated argument. But some people claim that if they did accrete during their history, there should be some X-ray, some signature into the X-ray background of the universe, which we don't see. So either primordial black holes don't exist, or they didn't accrete. It's up to you to choose. Let's assume that they exist. The first thing you have to take in mind, and it is the input of our work, is to take into account timescales, because of course you can have any density profile inside your galaxy at the center of the galaxy, but gravitational waves at some point will take over, and so you cannot grow your density profile indefinitely because your objects, primordial black holes, if you want, will start to plunge down. So you have to compare the timescale of gravitational waves. If you have any eccentricity, you add it, of course, as you know, with this integral, and the timescale of your two-body relaxation And of course, you take into account the age of the universe to stay below it to make any sense. And when you compare them, you get this nice plot, and where you can see where the time scales of relevance are the shortest. And so, as you can see, when you are about a few 10 to the minus 5 parsec from Sagittarius star, gravitational wave processes start to deplete any density profile that you might have there. And so you cannot grow it indefinitely where you would expect the maximum density near the more stable orbits, because, as I said, your density profile will be depleted. So how many of these objects would we expect to be there? Well, first of all, this would be an unperturbed density profile that we took as good, which is a spiked Navarro-Frankel-White, basically, which comes from this work from Silk in 1999. And I can go back to this slide after the talk if you need details about it. So basically, as you can see, it's just a bit more than, much more dense than an isothermal density profile. And it goes straight up until to the ISO, and then just, of course, goes down to 0. But this is the result of having time scales enter the equation. You will grow only up until to a certain point. Let's take this spike Navarro-Frankel-White that I just showed you. You would proceed and go up and up. But because of gravitational waves, of course, your density profile would be very much depleted. So you have some kind of a sink taking action. So your question is, how many of these primordial black holes are actually there in our galaxy? Maybe gravity can come to help, and they did, by looking at the orbit of S2 and its precession. The precession of the orbit of S2 gave our hints about the maximum diffuse mass that you can have, exceeding the one of the compact object, which is the supermassive black hole, of course. So here is Mr. Genzel presenting the same results during talk, and then you can see a bit better here. So what we're interested in is this upper limit, which is about 4,000 solar masses. That is the maximum extended mass from the closure of the orbit of S2. So you cannot have any more of 4,000 solar masses in whatever component that you want, apart from Sagittarius star. So, of course, you will tell me much of it can be gas, much of it can be stars that are too small to be seen. But let's just assume, for the sake of trying and see what happens, that all of these 4,000 solar masses are primordial black holes of one solar mass. So you get 4,000 objects. And so you look at the geometry of the problem, and you can infer that because these sources are mainly persistent, so let's say they're stationary, you can average all of these quantities out and end up with this very, very famous formula for the strain. And once you assume a time of observation, and for the sake of, let's be optimistic, let's say 10 years for LISA, which of course is not very realistic, but maybe we will achieve that. You get the number of cycles with which you can calculate your signal to noise ratio. And here you can put the sensitivity of your instrument. So of course, what we did in our work was to work with LISA and MURS. So of course, LISA is a famous artisanal lager beer, which comes equipped with its own sensitivity curve, which of course knows, has got its best sensitivity at around 10 to the minus 2, 10 to the minus 3 hertz. And MURS maybe is a bit less famous, but many in the audience know about it much better than I do, so a bit of a mix. It's a proposed future space-based detector, which is proposed to be launched in 2050, and should be covering the microhertz band. So that's why the mu in the name, and it's going to follow the orbit of Mars. So that's why the RS in its name. And here is its sensitivity curve. As you can see, at 10 to the minus 4 and 10 to the minus 5, there is a very big gap with the sensitivity of LISA, and this will turn out to be quite crucial to our results, because primordial black holes that might be orbiting Sagittarius star will turn out to reside exactly in that frequency band. So as LISA, we know, is going to be the most massive objects ever built by man. This record will be short-lived, as you can see, because MURS is this green and blue triangle, while LISA is the red triangle. but anyway, it's still just a proposal for now. Once you calculate your signal-to-noise ratio, you can, of course, distinguish between resolvable sources with this criteria and the background, which will follow, which we will enclose any source that are not resolved. And here are the results for LISA, which are very much not promising. You can see the same thing into the two plots. So basically, this is telling you that you got a 90% chance, basically, of never detecting anything based on the observation that we got from gravity. And here is the distribution that you can expect to have. This is the probability. So this is 1%, okay, of having a certain primordial black hole at a certain frequency, which in our very symmetric geometry is equivalent to having a certain signal-to-noise ratio. How about mu-RS?
Excuse me, Stefano, you have about 4 minutes left, just to let you know.
Because of the sensitivity, as I just showed you, is much better as at these frequencies. It's going to resolve many more sources. So this is showing you that you will have at least 100 of these primordial black holes detected. Of course, always assuming that all of those 4,000 solar masses go into primordial black holes of 1 solar mass, which is a big if. Maybe the background will go better, but it doesn't. So here is the sensitivity of LISA again, and which is zoomed for the relevant frequency band. And these are all the characteristic strains that are not from resolved sources, which are almost all of them. And this is the resulting distribution of expected signal-to-noise ratio from the background. As you can see, the threshold of 8 or 10 is up here, and you got a 1 in 1,000 chance of ever detecting a signal-to-noise ratio of the background above this threshold, so not promising. Much better it goes for mu-RS, which, as you can remember, has got the sensitivity curve going much lower in this frequency band, and most of these sources are actually inside of it. And so the background signal-to-noise ratio is much more compact and well inside 100 and below 1,000, which is very promising. So this is the result. You can maybe ask yourself, what happens if I don't want 1 solar mass primordial black holes? And we try that. What happens if I don't want a spike Navarro-Frankel white density profile? We try that. Don't get lost into this messy table now. Go into the paper and look inside it if you are curious. But basically, the take-home message is the numbers change a bit, but the trends don't, and the answers remain unchanged mostly. So of course, the next step that we are working on, and I'm almost done, is relax the no eccentricity assumption. Of course, if you look at a stellar component around Sagittarius star, you will notice that none of the stars have 0 eccentricity, so that's a very unrealistic assumption. And so the first thing you can do is try and assume a similar distribution in eccentricity for your primordial black holes, which is what we are doing. And we expect that the signal might jump up a little bit because you start to include higher and higher harmonics, the higher you go with eccentricity, and maybe you can enter the LISA band as well. So this is the first of the next step that we have got to take. But of course, you can do much better than this. You can think about some parameter estimation, because you can get a 1 solar mass object, but maybe it is not a primordial black hole. Maybe it is a star which you cannot detect, or maybe it is a very small neutral star that is not pointing toward you. So you don't know. Then you can extend the mass function. You can think maybe it's not just 1 solar mass primordial black holes. Maybe they have different masses. So you can work on that. Maybe you can think about what comes from the other galaxies in the local universe, from not just the Milky Way, but galaxy close enough that the signal in gravitational waves is not too much redshifted, so that you can actually detect it. And of course, you can also improve on quadrupole approximation, go to post-Newtonian orders, and refine your work. So as you can see, there is much to do. And if you're interested, you can join, and we will have something to do for you. Thank you.
Very nice. Thank you, Stefano. We have time for a question or two. Anybody in the audience?
Yes.
Yeah. So it's
very interesting. I am just curious because in principle you expect like a complete, mass function at least for stars, black holes, or all the, stars and stellar relics that are still there in the Milky Way. And if you, think about mass segregation, you expect the bigger black holes to segregate towards the center. And I expect those to be the bulk of objects very near to Sagittarius A star, and those smaller ones would, in consequence, tend to stay outwards. So I was wondering if you thought about that.
Actually, it is an excellent question, and for a month, this was our main scope. We were actually going to do the work around mass segregation, but the more we thought about it, the more we realized that the masses were not spread enough, not divergent enough from any stellar components. Yes, you have several solar masses, stars over there, but those are the ones that you can see. So mass segregation, there was also a work that came out that basically said, if you have one solar mass objects over there, they are probably not going to be any very much mass segregated as you would expect. So that was because one solar mass primordial black holes should be in some sort of equilibrium with a stellar component that is there, and they should not get too much mass segregated as you would expect in the first place. We can talk about it, but basically, yes, we went through this for a couple of months, and we decided that it was not the main focus, but still it can enter this list in the future, of course.
Thank you. Maybe we can talk again.
Of course.
All right, another quick question.
Marta has a question online.
So if I may ask, sorry if I missed it, but how important is the assumption that you actually have a spike compared to a standard NFW? Because my understanding is that spikes are very fragile, and it's very easy to perturb them, and their lifetime may not be very long.
It's not important at all, actually. It's just we based the decision to adopt a spike because many works before us try to get similar results assuming the spike. So we started from there. But when we try to look into different density profiles, we realized that the results didn't change by much. So the spike is not at all primary in importance. Plus, it gets depleted anyway. So the spike
right.
not even there. Gravitational waves, you're not going to have objects that close because they will be going down much faster because of gravitation than you would have otherwise with a normal spike.
Thank you.
All right, great. Let's give Stefano another round of applause. And our next speaker, I think, is remotely, and looks like they're here. Go ahead and share your screen, please. Our next speaker is Chiandong Paez.
Can you all see my screen and hear me?
Yes.
All right.
Yes, very well. Go right ahead. Thank you.
Yep. Just a minute. All right. Yeah. So hello everyone. My name is Chiandong Paez, and I'm a first-year PhD student at l'Institut d'Astrophysique de Paris. And today I will be talking about my current project in which we are modeling the multi-mission emission due to massive black hole mergers using a cosmological simulation. So first, just a very brief introduction. As you probably know, it is now well established that most galaxy nuclei host a massive black hole in the center. And so in our current picture of galaxy formation, galaxy mergers are a very common phenomenon. And when two galaxies merge, their black holes are expected to form a binary. which can eventually merge, and in the process emit gravitational waves and electromagnetic radiation as well. And these two sources of radiation can provide complementary information about the merger and also about the astrophysical population of black holes and mergers. So then our aim here is to model particularly this electromagnetic and gravitational wave emission from massive black hole mergers. And in order to do so, our starting point is kind of the physically motivated black hole population in the obelisk cosmological simulation, in which the formation and evolution of black holes is modeled consistently. So the obelisk simulation is a zoom-in cosmological simulation which follows the formation of a protocluster down to a redshift of 3.5. And since we're following an over density, we have many galaxies, and therefore many galaxy mergers and many black hole mergers to study. Another great advantage of this simulation is that it has very detailed black hole physics coded in. So in our case, black holes are seeded at high redshift, and then they're allowed to grow through accretion and mergers. From the gas accretion, they release part of the energy in the form of feedback. Also, we evolve the spin evolution due to gas accretion and mergers. And also, we also model the dynamical friction that they experience. And finally, we have very high resolution compared to what you have in cosmological simulation of 35 parsecs, which allows to resolve some of the relevant astrophysical processes. So in particular, what we do is to post-process this emission from gravitational waves and electromagnetic radiation that is expected from these massive black hole mergers into the simulation. So first, we model the gravitational wave signals and the parameter estimation by LISA using a Bayesian approach. And we also, on the other side of the picture, we also model the electromagnetic emission. On the one hand, due to the AGN-STD, for which we use due to the AGN accretion, for which we use a physically motivated AGN-STD. And from that STD, we calculate the emission in several bands. And on the other hand, we also model the emission in the radio due to the jet, and also due to the more unconstrained flare, which is expected from, for example, from GRMHD simulations. And finally, in order to assess the observability of the electromagnetic signals, we model the background galactic emission from stars in the case of the UV, optical, etc., and also from extra-binaries in the X-rays. And this galactic emission, in our case, acts as a contaminant. And finally, another effect that we have to take into account is obscuration, which is caused both by the gas in the immediate vicinity of the black hole and also due to the more extended galactic gas. So now I'm going to introduce you to some results. First, as a first approach, I'm showing here the overall population of black hole mergers in blue compared to the overall population of all black holes in galaxies, all black holes in galaxy nuclei in orange. And if you look at the left panel, you see the distribution of galaxy stellar masses, and you see that since galaxy mergers are more frequent for most massive galaxies, then also as a consequence, black hole mergers are more likely to be hosted by more massive galaxies. And due to the correlation between galaxy mass and black hole mass, we also have that merging black holes tend to be more massive than the overall population. And also as a consequence of the higher black hole masses, since more massive black holes tend to accrete at a faster rate, then you also get that as you see in the right panel, the merging black holes have a higher Eddington ratio. This is just an effect of the higher mass of the black holes, as you can see here. So if you restrict the range of the overall population to plot only the black holes which have a mass higher than so a mass in the range of the mass galaxy masses observed for the emerging black holes. So you compare kind of apples with apples, then you get very similar distributions. Now we turn to the gravitational wave signals. So here we show the results of our simulated parameter estimation by LISA On the top left plot, you can see the distribution of signal to noise ratio. And if we set the threshold for detectability at signal to noise ratio of 10, you can see that almost all events can be detected and to very good signal to noise ratio. And consequently, as you see in the right column, many parameters can be estimated to good accuracy. So in particular, you can see the chirp mass is recovered to good precision. Also the mass ratio. This is a bit that's the case for the redshift, and also the spins. The precision of the spins can be recovered to decent precision. But the bad news is that the scale localizations are generally poor for our sample. And as you can see in the bottom left plot, with almost 2/3 of the population of mergers having a scale localization poorer than 10 square degrees, and this makes potentially very difficult that gravitational wave parameter estimation can guide the follow-up detection of electromagnetic counterparts. So now we turn to the side of the picture, which is the electromagnetic wave emission. Here, I'm plotting on the y-axis the emission due to black holes, and the x-axis the emission due to the galaxy. And in the left panel, you have the emission in the UV. In the case of the galaxy, this is due to the stars. And the right panel, the emission in the X-rays, which for the galaxy is mainly dominated by X-ray binaries. And the luminosity of X-ray binary is essentially given by the star formation rate of the galaxy and the stellar mass of the galaxy. So you can see in the left panel that in most cases, or no, almost all cases, in the UV, the galaxy strongly overshines the black hole, which makes potentially very difficult is detectability of the post-merger black holes. And also in the right panel, you can see that the prospects in the X-rays are much better. So if we use the parameters that we obtain in our simulation, there is black hole masses and accretion rates that we obtain in our simulation, then we get that 20% of the events of the post-merger AGN can be detected. Well, can be brighter than the galaxy, and in a hypothetical scenario in which the merger causes a higher accretion rate, a rebrightening of the AGN, that essentially makes the black hole accrete at the enter rate that is shown in the red crosses, then you get that more than 50% of the black holes shine brighter than the galaxy. And now next we explore the two populations lying above and below this line. So in blue, the undershined black holes, those that shine brighter than the galaxy, and in orange, those are overshined by the galaxy, overshined black holes. And you can see that there's an interesting distribution by modality in the undershined black holes, since you have in the one hand the very high mass galaxies, which have comparatively very high black hole masses, and therefore these are easy to overshine the galaxy. And on the other hand, you have the low mass galaxies, which have low star formation rates and consequently low luminosity of X-ray binaries, and but they have black holes close to the seed mass, so they're also likely to be brighter than the galaxy. So this is the cause of this bimodality here that you can observe, and which consequently can also be observed in other distributions, such as the distribution of black hole mass, star formation rate of the host galaxy, and the mass ratio. Also, another two factors that aid that the black hole shines brighter than the galaxy is, on the one hand, that the black holes are overmassive with respect to the galaxy, of course, and so we expect black holes brighter than the galaxy to also be overmassive compared to the galaxy. And on the other hand, also high accretion rates, so high amounts of accreted material that can release energy, also help the black holes to be brighter than the galaxy. And finally, just to conclude, here I show the radio observability of the black hole merger remnants. I don't know if you can see here in the left plot, there are points and crosses. and the points correspond to the standard jet of the post-merger black hole. The courses correspond to the flare that is theoretically expected from GRMHD simulation at the time of the merger. And you see that for the case of just the standard jet, with future instruments, only 1% of the 1% of our sample can be detected, which corresponds on top of that to the very high end. So black holes with 10 to the 7 solar masses, more than 10 to the 7. And these black holes also tend to experience mergers with low mass ratio, and the combination of high masses, very high masses, and low mass ratio gives generally very poor signal to noise ratios in the gravitational wave parameter estimation. In the case that we have this theoretically expected flare, then which is much brighter than the jet, you can see that that the prospects for detection increase very much, and a larger amount of the population can be potentially observed. But this effect is greatly unconstrained, and so yeah. So yeah, I come here to the end of my slides. Leave you with a summary of my presentation. Thank you very much for listening. I'm happy to take any questions.
All right, great. Thank you very much. We've got a few minutes for questions. Anybody in the audience there? Go right ahead.
I have a question from at the very beginning when you show the population of all black holes merging. I was just wondering, the merging black holes, these are like all black holes merging, or just the ones who are bright AGNs?
This is all the black holes. Yeah.
No below 10 to the power of 8 merging in this.
Sorry, I didn't catch that.
So there are no black holes below 10 to the power of 8 solar masses merging.
10 to below 10 to the power of above 10 to the power of 8. You mean?
Yeah.
That's the mass in stars.
Okay.
Yes. So there's a stellar mass in the left panel and the black hole mass in the middle panel.
Yeah.
Yes, and essentially we have no black holes with a mass lower than 10 to the 4, because that's our seed mass in the simulation.
Another question possibly from the audience? I don't see anybody on Zoom right now with their hand up. If not, I have a question.
Yeah, go ahead.
Thank you. I was wondering, I don't think I saw plots of the redshift, or like histograms of the redshift for these things. Was there, I guess I'd be interested to know which black holes were at which redshift, like a scatter plot of their mass versus the redshift or something, or was that not?
Yes. No, yes, I didn't show it due to time constraints, but that is indeed an interesting thing to look at. Yeah, so as you expect, you have some trends with redshift, because, for example, well, on the one hand, you have larger amount of mergers at lower redshift, and also at lower redshift is only when you get to form these more massive black holes. So the mergers with very high mass only occur at low redshift. So yeah, if you plotted mass against redshift, you will see that only the high mass redshift only tend to occur at low redshift. And yeah, consequently for these kind of two populations of undershine and overshine black holes, then one of the two populations, the population of more massive mergers, tend to occur at lower redshift compared to the other lower mass black hole mergers, which since are close to the seed mass, and you can create them at arbitrarily high redshift, well, not necessarily arbitrarily, but then you get them at a very much more extended range of redshifts.
Thank you. If there aren't any other questions, I had one more. Does this simulation allow for spin evolution of the black holes?
Yep.
And so it's just like is it just kind of increasing as they accrete, the spin magnitude?
Yes. So yeah, basically we include the spin evolution in two ways. So one is through gas accretion, of course. So the spin tends to the spin evolves by just accreting the angular momentum of the gas, and then it also can evolve through mergers. So since you can merge with a black hole that has a different angular momentum, spin angular momentum, then the angular momentum is going to evolve due to the merger, and this is just taken from some fit to the numerical relativity simulations of black hole mergers.
Does it just assume that the spins are aligned in the direction, are aligned with
the spins of the two merging black holes? You mean?
Yeah.
No, we don't make any assumption. We just let them evolve in the cosmological setting, and we take the spins that we get from the simulation.
But in terms of the direction of the spins,
yeah, the direction is also evolved in the simulation.
Interesting. Okay, thank you. Thank you very much. Okay. Any other questions for Shi before we move on to our next speaker?
None from the room?
Alrighty. Let's give Chi another round of applause, please. Great. Our next speaker, it looks like, is in person. His name is James Monday. And James, go ahead and set up, and the floor is yours.
Thank you very much. Okay. Hello, everyone. My name is James Monday. I'm a first-year PhD student from the University of Warwick, and my talk today is based on the shortest period binary star system named HM Cancri. It's maybe a familiar name in this group. I'll go on to that in a second. A bit of background on the source. It was first discovered just over 20 years ago from a periodic X-ray modulation of period 5.4 minutes. For a long time, it was not known what the configuration of the source was, but the evidence now points towards it being a double white dwarf binary star system. Continued observations in the optical and the X-ray domains have revealed that the frequency of the source is increasing, such that the frequency derivative is positive, and that the binary is currently in spiraling. Onto the image shown on the screen, with it being a double white dwarf binary, the two stars are separated by just 0.1 solar radii, so it's really, really compact. Unfortunately, the source is too dim for a Gaia magnitude or parallax. It's too dim for a parallax or motion, such that we really don't know where it is in the galaxy. We just know it's pointing telescopes to, and with this, we don't know star masses either very well from follow-up studies. Why is it useful for this group in particular? Well, it is going to be the brightest verification binary for LISA upon deployment, where after 4 years of observing, signal flow is going to be over 200 for an assumed, not known, but assumed distance of 5 kiloparsecs, as shown in the circle on the graph. It's so bright that it might even be found within weeks. So this is very useful as a calibrated source and for initial tests of LISA. There have been multiple other sources since the work of Kupfer and collaborators 2018, mainly through photometric surveys to try and find more systems that can use these verification binaries. So that brings me on to my study, or our study. What we have done is observed HM Cancri over 20 years of observing with high-speed photometry from the hypercam or ultracam instruments based on telescopes in the world. In the figure, I'm just showing a general light curve. So this is how the light deviates to function orbital phase for 5 different filters, with the ultraviolet at the top and infrared towards the bottom. The idea of us doing this is to measure the orbital decay, where if we look at just the peak flux now, we can say in the future at every n integer cycles, we're going to get the same peak flux if it's a constant orbital frequency, or if there's any deviation to that, we'll see the peak flux earlier or slightly later. If that method sounds familiar, it's because probably you've heard of the Hales-Taylor pulsar, where a timing difference in the arrival of pulses gets a really nice orbital decay like so over multiple years. And this can be a little bit misleading, because if we were going to do a blind search for a frequency of the system, we would have a straight line going through the middle, such that the residual is a parabola. And the residuals of that parabola to the data is between 5 and 10 seconds. Applying the same kind of method to HM Cancri, we get a parabola like so in residuals, where instead of 5 to 10 seconds, HM Cancri is actually deviating by 5 to 10 cycles, where each cycle is 300 odd seconds. So that should give you some perspective of how much orbital decay is going on. We can quite clearly see from the residual fit that a constant frequency does not well fit the data at all, and we need higher order terms, such that if we were to go for a frequency derivative as well, rather than 5 to 10 cycles, we're finding 0.05 cycles residuals. This is already known, like I said at the start, where the system is inspiraling, but how 20 years of data has benefited us is that for HM Cancri and HM Cancri alone, you can go one further and try and find a second derivative term. And this gives us insight on how the binding may evolve into the future. And on the screen now, it's shown as a solid grey line between the data, where if we were to yank the number out of this, we would find a significant fit to 4 sigma, and this agrees very well with X-ray measurements. So we have a positive frequency, we have a frequency derivative that's positive as well, so the system's inspiraling. But what's really interesting about this result is that the second derivative is negative. If one were to expect pure GR evolution, then as things get closer, they accelerate, and the second derivative would be positive. An explanation for this is that instead of the binary merging, it may be restabilizing against mass transfer, and then going to widen on larger orbits. So that's fantastic. Now, there's 20 years of data to find a second derivative term, which is unique for HM Cancri, the verification binaries. And now I want to see if I could model the system in serial evolutionary codes. So we have the frequency, the derivative. So immediately from the graph shown in the picture, the solid black line represents the chirp mass of the system, allowed system parameters. There's a caveat here that would be the case of a detached system, so no mass transfer at all, where because there is mass transfer, all we can do is reject the white region, and everything in the blue is still allowed. So the masses are unconstrained until further analysis. That brings me on to MESA models. So MESA is a stellar evolutionary code where I perform this action, modeling to realistic styles, or styles of realistic structure, to see if I can reciprocate the observations. The graph is quite busy, so I'll explain what's going on here with the cursor for people at home as well. We're starting from the right at larger orbital periods or smaller frequencies, and evolving to the left. Each different color is a unique set of system parameters for input models conditions, and the gray crosshair here is the current state of the system, so where we see it in present day. We can see at the start, the curve is pretty consistent with all, going from the bottom right up to here. And this is because the mass accretion rate is relatively low, and GR decay is still the dominant factor. As we approach the time of current day, these models show that the second derivative term is negative, where, so I should have said on the right here is the first derivative term. So that begins to decrease, such that the second derivative term is negative, and I find some compatible models within the range of the donor and accretor masses displayed. This is great. I found a negative second derivative. Can I also find the magnitude of that to be consistent with the observations? I'm showing that on the right now. So once again, the colors are the same, and the gray cross there represents the current state of the system, where on the Y is the second derivative positive. Overall, it doesn't do half bad. I can well reciprocate the observations for an EOM donor star and a high mass accretor. And furthermore, we obtain a measurement of detection of hydrogen in the spectrum, and the predicted hydrogen mass at this point is consistent too. Something I want to put forward with this is, although we're catching it just left of the crosshair, when I do the evolution of the whole star system, we are only catching the final 2,000 years before a change in orbit, where the time before that is on the scale of 100,000 years. And a glaringly obvious thing here is that we have had a huge selection bias, most likely, and to say that where are the other star systems in that orange region that would also be accreting. Hopefully Lisa will find some if they're not visible with X-ray source. So to conclude my presentation, the 20 years of data have uniquely been able to find a secondary term for HM Cancri and far improve it as a Lisa verification source, such that period decay is better defined and passes previous studies. Although in this case, I found that we're on a turnaround point where the binary is evolving to a maximum frequency or a minimum orbital period. And this means that the observed Lisa chirp mass is going to be similar to the actual system chirp mass, which may not always be the case. For HM Cancri, they are both representative. So Lisa would find it, but maybe not for all systems. And to emphasize the point of HM Cancri here for the community, after the whole study, it's still the brightest verification binary that can be used for the Lisa spacecraft. And that's all I've got. So I encourage any questions.
All righty,
Yes.
very nice. Oh, go right ahead.
I have a lot, but I'll ask one and save the rest for the coffee break. So it is pretty amazing that you managed to find with the binary evolution models a very similar bounce back period. That depends very, very strongly on the angular momentum that you're seeing.
Yes.
What is lost, of course.
Yes.
What was the model that was considered, and what are other models that we tried and didn't work?
Sure. So I didn't focus on the set side too much for this, but I can answer your question completely. I'll start at the beginning and I'll go forward. So if you were assuming normal mass transfer in a binary, there's a wider separation, you'd expect mass to flow into an accretion disk around the accretor, from the donor onto the accretor. And the model for this is that over time, all angular momentum transferred to the accretor is repumped into the orbit of the binary. That's not lost. In the case of HM Cancri, like I mentioned, it's only 0.1 solar radii apart. We don't have an accretion disk forming, and as shown on the image just there, you have direct impacts going into the surface of the accretor. And this itself has its own angular momentum sink. And when you look at my models, as you suggested, we can see the characteristic of where there's a transfer from accretion fed or direct fed accretion, so either onto a disk or onto the surface, in the green model where there's a kink just there. And besides that, it's just GR radiation and there's some stellar mass loss that contribute to the angular momentum change.
That's really nice. It's really, really cool to see that. I'm impressed. I hope the next one is B407 wall for you to tackle, but I know it's harder. But anyway, so the masses you're having for this model are very different. And point taken that the Kulov's masses might be very uncertain, but the masses you're having are very different what Kulov's had from his assumptions on the velocity and everything.
Yes.
So now, assuming you take your masses, the ones you have, and then go back to the spectroscopy what Rulov's did, can you say more about if this is consistent, and maybe say something about the inclination angle, or can you now?
So not so much the inclination angle, but you can use this to. There's a bit of a caveat here where I'm showing the case for a initial hydrogen mass of 6 times 10 to minus 3. This changes models quite a bit, as well as the temperature of the donor star can alter that.
Okay.
So we obtained HST spectra for the object, but it's not good. I don't trust it enough to get a donor temperature, so that's not completely constrained. So we're going to try and get more is the plan. But in terms of the actual location, the accretion spot, so there's a relative phase difference between the X-ray and the optical source. It's close. It's very close in these models. But the point is of presenting these that the observations can be fit relatively well, but not entirely. So more constraints are needed.
That's okay. That's fine. Cool. Really nice.
Valeria, did you have a question?
And Nate, do I have like a minute for a question? Otherwise, I can speak to James later.
I think I've got a couple minutes. Go right ahead.
I had a comment and a question. So the comment would be, I think that HM countries are XJOs. So then it becomes even more important in gravitational waves because it will be the the calibration source for Tianjin mission,
Okay.
and the Tianjin is actually designed to point towards ancient country.
Okay.
But I don't know exactly why, so maybe it would be interesting for you to look at this.
Honestly, I'm not familiar with that, but I appreciate it. Thank you.
Look, I can explain to you. And this tiny question that I had is like, sorry, I haven't done math, but will the period of the ancient country change significantly in 15 years when Lisa will fly?
Not a huge amount. So the gap in this section here, when it decreases, is just 1,000 or 2,000 years or so, which is a bit past us. But a difference is, like I can show, that will be detectable. So backup slides. It's the mass transfer rate. So as it gets a bit closer and closer, the mass accretion rate will increase, and whether we would expect the accretion luminosity to increase too. So we might see a visual and X-ray increase over time. But for the period itself, it's small. As I said, for the second derivative term, we're only seeing that after 20 years of observing, and the relative decay is, it probably won't be viewed in the Lisa time frame. Is that all?
Nate, is there time for any more? I have a little question. If this.
Yeah, go ahead, go for it.
So, I don't know much about these sources, but is there much chance that the gravitational wave frequency could sort of, change randomly due to changing accretion rates over the observation period? So the reason I ask this is in LIGO, when you look at the continuous wave signals from rotating neutrons in limit sexual boundaries, there can be like a change in the accretion rate, and
Sure.
you may have to change, like you can move around the bins in frequency.
Sure.
So I just wondered if this is a similar situation.
A bit. I don't want to put too many slides in, but I'm going to do it anyway.
Of course.
Sorry for the clicking. There will be 2 seconds. So a result of this from free adjacent lights is that we actually do witness a change in the received light, the light level of the system, such that it's likely flickering. So yes, there is a change in the mass accretion. Have not been able to describe that very well yet, except that it is a case. But these are from data from the VLT telescope for 3 adjacent lights and very similar observing conditions, where the red curve is just for the top, which is 1/9/2005. The second one is the day after that in black, and we're seeing red and black completely different. Well, I say completely, it's slightly different, but as indicative, there might be flickering, which is very typical of cataclysmic variables.
Yeah, thank you.
No worries.
I think that's it from the room.
Alrighty, thank you. So, excuse me. Thank you very much, James. Let's give him another round of applause. Alrighty. Next, we have another in-person speaker, Martina Toscani. Please hook up your stuff, and the floor is all yours.
I'm coming. Sorry, it's just some little problem with to share the screen because it's the new computer.
Oh.
Up to work. Sorry. 1 minute.
Okay.
Yes, okay. Sorry for the inconvenience, but when you're out live, there are like this kind of problems. Tell me when I can start.
Nate?
I can start.
I'm sorry. Yes, go ahead.
Okay, so good morning, everyone, and thanks for the opportunity to be with talk today. My name is Martina, and I am a postdoctoral researcher at the Laboratoire des Infinies in France. So with this talk today, I would like to present what has been my main research topic as a PhD student in Milano, and this topic is actually also something that I still continue to do in part as a postdoc. So this topic is the study of tidal disruption events, in particular through gravitational waves. But let me start from scratch. Okay, so what are tidal disruption events? Well, TDs occur when a star orbiting around a massive black hole is disrupted to the black hole tides that overwhelm the stellar self-gravity. And after the disruption, we expect roughly half of the stellar debris to circularize around the black hole and starts to accrete onto it. Actually, so far, these events have been one of our most powerful tools to unveil the presence of massive black holes in the core of quasar galaxies. Why? Well, because during the accretion of material to the black hole, we have production of very luminous electromagnetic flares. And as a matter of fact, today we have been able to observe already 100 tidal disruption events, mainly in two bands of the electromagnetic spectrum, X-ray and opticals. Yet, the potential tidal disruption event is much bigger than this. As a matter of fact, we also expected these events to emit high energy neutrinos from the later stages of the event. And there are two potential candidates of astrophysical neutrino detection quantities. But we also expect them to emit gravitational waves. And in particular, we expect gravitational wave production during the whole process. But within this talk, I will focus on the gravitational wave monochromatic burst that is associated to the disruption of the star, because it's the strongest gravitational wave contribution that we expect from the sources. But let's try to give some numbers. So this burst has a strain and a frequency that can be approximated with these two formulas that you can see in the top of the slide. And if we consider what is called the standard tidal disruption event scenario, that is a sun-like star disrupted by a 10⁶ solar mass black hole at 20 megaparsec from us, we can expect a strain that peak around 10⁻22 with a frequency around 10⁻4 hertz. But actually, this frequency can increase and reach the ditch-Earth regime thanks to the parameter beta, which is a dimensionless parameter that quantifies how strong is the disruption event. Or in other words, how close the star is to the planet. So this information is actually quite interesting for us because it's telling us that the tidal disruption events emit gravitational waves in the regime where the future space-based detector will work. For sure, LISA, but also Tianqi, and maybe also other possible detectors like the SIGO, AIA, and also the Lunar Gravitational Wave Antenna. But now that I hope I convinced you that tidal disruption events emit gravitational waves, let's try to understand what are the features of this image and what kind of information we can understand from its possible detection. So let's start with gravitational wave signal from individual tidal disruption events. How can we understand how this signal looks like? Well, what we need to do is, of course, a numerical work along the way to answer this question. And this is what I was trying to do during my PhD. So what I did, I took an already existing code, an HPH code fund, that is particularly well suited for simulation of 3D non-axis symmetric system like header disruption events. And within this code, I implemented a module for the derivation of gravitational waves. So basically, my algorithm is calculating the second time derivative of the moment of inertia of the system on fly, that is during the simulation, and is using this information to calculate H plus and H cross. So I implemented this algorithm, I tested it to verify that it was working properly, and then started to apply it to see how the gravitational wave signal quantity was like. So here you can see the gravitational wave, signal from the standard PV scenario, assuming that we see the system stays on. And actually, this was already great news because this plot here was in good agreement with very few previous works that were already trying to provide this signal numerical prescription. Yet the very interesting thing was then to use this tool to start exploring the parameter space and so see how different values of the parameter that describe this system could affect the gravitational wave signal. For instance, I consider different black hole spin, different inclination of the stellar orbit, different beta parameter, prograde and retrograde orbits. So I did quite extensive studies that you can find if you are interested in this topic, or in the paper, this Technical 2022, or in this website, the Mountain in the Circle, where I collected all the gravitational wave signal from the simulation I did. And the idea is actually to continue to update this library to have a collection of gravitational wave force quantities as comprehensive as possible. Unfortunately, given the time, I will not show these results, but just let me say from these signals, we can extract information, in principle, on the dynamical properties of these events. But a recent study, well, actually, I was also one of the authors, showed that, if from one side, we are sure that with the HRX observatories, we will be able to see thousands of header disruption events with gravitational waves. With LISA, the situation is a bit more complicated. And actually, it's possible that LISA will be able to see gravitational waves that involve very massive stars, which are very close to the black that destroy the stars. But these kinds of events are quite rare. So it's a bit unlikely. For this reason, it can be interesting not to focus just on the signal from an individual TD, but instead the signal from the population of header disruption events. That is the gravitational wave background. And to understand how this background looks like, I did an analytical computation together with Verena Rossi, Giuseppe Rodato, and our idea was to distinguish between two classes of header disruption events. What we call the nuclear TVs, that are the classical TVs, main sequence stars disrupted by massive supermassive black hole in the course of galaxy, and globular TVs, where instead we consider white dwarfs disrupted by intermediate mass black hole that we assume can live in globular clusters. So we did a calculation after, of course, some assumption, and what we got? Well, actually, we got two main results. The first was that this gravitational wave background signal has a particular shape that is proportional to the frequency 2 minus 1 out. This is something true for both the classes of header disruption events that we consider, and it is actually a consequence of the impulsive nature of the gravitational wave signal of these sources. As I told you, it is a burst. And then the second main result that we got was that actually, as you can see also from the plot, the background generated by the population of nuclear TVs is in a frequency window where there are not, for the moment, interferometers enough sensitive to detect it, maybe URS, but not LISA. But the situation is different if you consider the background generated by the globular TVs because in this case, this can be a very promising source for the HER's observatories. And a possible detection can give us important information about a possible distribution of intermediate mass black hole through the universe, at least up to redshift 3, and also information on how globular clusters are distributed in the galaxies. But maybe there is still some hope for Lisa. This is what I try to desperately look during my postdoc. What I'm doing right now is try to apply strong lensing to the gravitational wave emission generated from tidal disruption events. So the idea is quite simple. We assume that there is a lens that is a massive object between us, the observers, and the sources. And this lens is deviating the original path of the emission from this source. So I'm considering that the possible lens that we are interested into are the galaxies in the universe. And I consider in the case of strong lensing, of course, which means that there are two main consequences that can be interesting: multiple images of the source and magnification of the source. So in practice, what I'm trying to do right now is to calculate this quantity, that is the probability that my population of sources that I assume at redshift Z is magnified more than mu by the population of lenses I take into account. And as you can see, to calculate probability, there are two main terms that we need to derive. One is the little p, which is the density probability that a generic source at redshift Z is magnified more than mu, given a specific lens distribution. And then there is the quantity Dn over dz, which is related to, as you can see in the integral, to the number of sources per unit of signal-to-noise ratio per unit of redshift. So this is actually the part where enter the information of the instrument we are considering. And I'm doing this analysis considering Lisa, but also all the other possible interferometers that will work.
Excuse me, Martina, you have about 3 minutes.
Okay, there is time. And actually, this is also the part where there are more possibilities to do various hypotheses and to have more fun, because I need, first of all, to calculate that the N over the Z, I need to create a population of tidal disruption events. And it is something that can be modified if I consider different distribution of galaxies, different distribution of stellar masses, can be more or less sophisticated. I mean, there are many things that actually it's possible to explore within this calculation. So let me conclude saying that for sure, in the upcoming future, we will see tidal disruption events with gravitational waves. And actually, for sure, there will be also multi-messenger observation of tidal disruption events. The most likely interferometers that will see these sources will be the DHR's observatories, but also LISA as a possibility to see these events. And still, they are very funny sources to study. And I hope that the gravitational wave community can put a bit more of interest in these sources that so far were a bit in the corner and not very considered, unfortunately. And this is all from me. Thanks for your attention.
Very nice, thank you. Questions from the audience?
We have one here.
Just in the population model you are trying to build, and all the possible types of TVs, or you're focusing more on
Yeah, and when I'm doing both.
Okay, so
yes. I mean, just right now, I'm just doing main sequence stuff because I just started this calculation, but I also want to do IMDH on my book.
And IMDH is also
yeah, actually, also that. Yeah, actually, I would like to consider IMDH a massive black hole and not a star, and white dwarf engineered massive black hole.
Okay, looks like Shane from Zoomland has his hand up. Go right ahead.
Yeah, thanks. So that was great, Marta. I had a question about the confusion limit. So slide 8 or so, you had showed the spectrum underneath all the perspective sensitivity curves. Yeah, this one. Yeah. So the green area is the region where the confusion spectrum would lie, depending on the mass of the IMBH that the TD is happening around.
Yeah, it's somewhere within this green area. Actually, it's a way to quantify our uncertainties on a possible distribution because right now we don't really know if intermediate mass black holes do exist and what is their mass distribution. So I did some hypotheses, and for this reason, I light this green area to say this background is somewhere within this green area.
Okay, so then I think what strikes me about this is 10 to the 5s almost certainly exist, and that's getting, let's say, precariously close to the Lisa sensitivity. So I was wondering about the hard cutoff at the low frequency side of that. What's the plausibility or what's the worry that that confusion is actually going to be above the Lisa sensitivity in the regime where we're going to look for traditional emeries?
What's the worry?
Well, I mean, this is a hard cutoff, I assume, because of your simulation. So there's some curve. So is that line going to turn over below the sensitivity curve, or is it going to go above the Lisa sensitivity?
Of interplay between the fact that the frequency is very shifted with respect to the frequency source, is the observed frequency, and also the beta parameter, which play a role in it. Because so these lines are that extend in the frequency domain depend on these two things, zeta and beta, because we are considering that this is a monochromatic.
Right. Okay.
So yeah.
I'll think about this some. Yeah.
Okay, great. Let's give Martina another round of applause. Thank you. And the last speaker, our final speaker for our session today is Federico Cantarini. I believe he's joining us remotely and he's here. So go ahead and share your slides, please. Federico.
Yeah, here I am.
The floor is all yours. Take us away.
Can you see them?
Yes.
Okay, thank you. Hello everybody, I'm Federico Cantarini. I am a PhD student at Insubra University in Como, Italy. Sorry if my voice is down, I got a sore throat, but I hope you can hear me well. So in the next 10 minutes or so, I will present some work that I have been doing over the last 3 years, along with the Milano Bicocca group, concerning the latest stages of the evolution of massive black hole binaries using numerical relativity simulations. And so, massive black hole binaries. We have already discussed the topic roughly these days. Also, Chiam talked about this before, so I'll be quick here. LISA will hopefully detect the late stages of massive binary spiral and merger, providing precious information about black holes, such as their masses, spins, and so on. If we had the chance to perform synergistic electromagnetic detections, we would be able to address plenty of scientific key questions like the ones here. Still, to be able to do this, we needed to get a better understanding of these systems. We know from our current models of galaxy evolution that most galaxies host a massive black hole in the center, and since galaxies are supposed to merge across cosmic history, it's reasonable to expect that binaries of massive black holes would form and eventually merge. So if we wanted to exploit the chances to do multi-messenger, though we must get better insight on what's happening in the vicinity of those systems. As Elisa said on Tuesday, to date we lack firm predictions on the electromagnetic signal emerging from these binaries, and also we don't really know what kind of structure of gas structure is to expect in their vicinities. Thus, we need better theoretical modeling of those sources. And now I'm showing you for like the third or fourth time this nice figure. displaying the evolutionary path of these binaries. And such evolution covers a huge scale, as you can see, both in space and time, and its modeling requires diverse techniques. And my work addresses the very latest stages of this, that is the latent spiral, the coalescence, and the formation of the black hole remnant. And in order to study those stages, we cannot rely on approximations, for example, post-Newtonian, but we needed to solve the Einstein's equations of GR coupled with the hydrodynamic equations, Maxwell's equations, and so on. And to do so, one can rely on techniques of numerical relativity to perform full GR MHD simulations, and thus study the evolution of plasma, magnetic fields, and so on in such extremely curved and dynamical spacetimes. So in this slide, I'm giving you a super short course on numerical relativity, just to give you the idea of what's behind it. It may look a bit technical, but please don't look at the equations. So we all know that GR is a 4D theory in which the time coordinate plays no paramount role. Problem is we can't evolve these equations. The physical systems, they need to evolve in time starting from given initial conditions. And this is simply not possible in the 4D formulations of GR. So the solution is to recast the equations of GR into the so-called 3+1 formalism, and which basically means that we will split space-time into 3D space that are evolved in time. And as you can see, the equations get more complicated, but the good thing is that the two formulations are perfectly equivalent. So with the aid of numerical relativity, we can model massive binaries in full GR. And now, one must keep in mind that this full GR MHD modeling is still in its youth. Over the last decade or so, there's been a number of works that have progressively added new layers of physics on what had been done before. And in this slide here, I'm giving you some history about massive binary simulations. And all the simulations I'm talking about here adopt the same approach, that is modeling in 3D the latent spiral, very close to coalescence, not evolving a second binary environment, but seeding all the domain with a magnetic field that is assumed to be anchored to a distant second binary disk. And also, they all consider equal mass binaries initialized on quasi-circular orbits at very small separations already in the GW regime. And little by little, simulations, as I said, are getting more and more sophisticated. And in his seminal paper of 2010, Palenzuela performed the very first simulation of merging black holes with a magnetic field in the force-free regime, showing for the first time that collimated electromagnetic jets can form over each black hole across in spiral, and then merge into a larger, more powerful jet. And later, more complex configurations were considered by, for example, by Bruno Giacomazzo, my supervisor, by Kelly, who performed ideal MHD simulations. That is, they considered a plasma surrounded black holes with non-negligible inertia, and their work is still considered non-spinning black holes. So over the last 2 years, I broadened the parameter space and studied binaries of spinning black holes to explore, the effects of spin onto the mass accretion rate, onto the gas flow, the electromagnetic emission, and so on. More on this in a minute. And after studying both aligned and misaligned spinning, now my group and I are studying unequally mass systems with Q between 1 and 5. And also, I just began implementing a code for cooling with Giacomo, a master's student who just began his thesis. So let's say we got big fish to fry, and we hope to deliver interesting new results soon. Then talking about results, in these last minutes, I'll give you a short overview of what we found in our work. But first, I need to briefly mention the kind of physical information that can be extracted from our simulations. So First, of course, we extract the GW signal, the gravitational strain. Then we keep track of all the matter field evolutions. So we follow the three-dimensional evolution of the plasma density, velocity, pressure, and so on. And also we track in a self-consistent way the accretion rate onto the horizons of both black holes across the spiral and after the coalescence. And finally, we also follow the evolution of the magnetic fields and the emission of electromagnetic energy in a jet-like fashion that closely resembles the Blanford and Znayak mechanism. First, here's some pictures about the evolution of the plasma around black holes that span several values of the initial magnetic field and of spins. And I found that when the gas is seeded with the magnetic field, the gas dynamic, the gas structure dramatically changes. That is, if there is no magnetic field, the accretion flow is basically Bondi-Hoyle Littleton 1. But when the gas is seeded with magnetic field, its structure rapidly changes, and we see that two little disk-like overdensity form around each black hole. And we explored this effect, tracking the evolution of the Mach number, as you see on the bottom left figure, and the circularity parameter defined here. And in short, we found that when a magnetic field is present, the gas is faster, it rotates more, and it settles into a disk-like fashion. And in this slide here, I just want to emphasize what I just said. So you can see three-dimensional snapshots of the binary evolution with a magnetic field. Sorry guys, I just read the chat, so I hope you can hear me now. Can you please confirm if you can hear me?
Yes. I think we had problem only in the room, so people from Zoom should be fine.
Okay, thank you. As I was saying, in this slide, I'm showing you three-dimensional snapshots of a binary evolution with magnetic field. And as you can see, in the beginning, the accretion flow is very Bondi-like, but soon, after a couple of orbits, it becomes more and more thin, and in the end, you can see that a proper torus has formed. Last, I want to show you these plots. Because as I said, I use a dependence of the accretion rate, its magnitude, on the spin, both in magnitude and orientation. The same result was found independently by another group at RIT, which considered black holes with the spins aligned or anti-aligned with the orbital angular momentum. And this is encouraging because, since I think it's compelling to have multiple groups with diverse codes working on the same systems. Also, we found that across the spiral, the accretion rate can be strongly modulated, and I'll come to this in a second. I also studied, as I said, the emission of electromagnetic energy as a point luminosity, and my results are consistent with all the previous works by Palenzuela, Mosta, and some that the electron Znayak. Sorry, I see that the connection is not stable. I hope you are still with me. And I observed that the peak luminosity does not depend on the initial value of the magnetic field, but it depends a lot on the spin, on the magnitude of the spin of the remnant, which again is consistent with Blanford and Znayak. Still, what I most found interesting is this. So I noticed that the accretion rate and so I investigated these modulations performing a frequency analysis, that is a power spectral density and PSD wavelet analysis. And I found that in certain configurations, the accretion rate and luminosity exhibit this. But as a chirp, they basically display the same evolution time and frequency as the gravitational waves, which is very interesting for multi-messenger observations. And so to conclude, I again stole something from the slides of Elisa's. And so we know that before lasers, we need to get a better theoretical understanding of the sources. We need to be able to distinguish between different sources. That is, we must be able to discriminate between, let's say, a changing look AGN and the massive binary. So, you know, so far as I hope I have shown, we've done a lot. It feels amazing. I think there was the very first simulation of black hole binary in GR. It feels like, yeah, to me, but anyway, there is still much more to be done, and we need to be able to make firm predictions about the electromagnetic emission emerging from massive binaries, and thus we must improve our simulations. We must consider more realistic systems with radiation transfer, with ray tracing, and so on. Because this way we will be hopefully able to exploit the most from LISA. And that was all. Thank you.
Thank you very much, Federico. Are there questions from the audience?
Yeah, there's one from.
Yeah, go for it.
I might have missed this, but what is the physical motivation for the initial conditions for the gas? I mean,
yeah. You know, basically, there are two reasons to justify the initial conditions. And the first one is that if we wanted, it's just computational convenience, because so far it's not possible to evolve in a self-consistent manner a certain binary disk. You know, simulations where the binary just decoupled from the circumbinary disk and it goes straight down to coalescence is still not computationally feasible. So that way we considered just the gas portion very close to the black holes, and we started the simulation with the gas assumed as a uniform gas, and after a couple orbits it relaxes and settles down into a more realistic configuration. But right now we are working onto that, because we are aware that a more realistic physical configuration is is required to get the most from the simulation. So we are trying to evolve in a self-consistent manner a circumbinary disk in order to not having a uniform gas, but having a mass accretion flow caused by the individual gas streams from the inner edge of the CBD to the mini disks and so on. So we are onto that at the moment.
Thanks.
Another question from the audience. I don't see any hands up on Zoom land. Oh, I see one hand up, sorry. Alexi, would you like to go ahead and ask a question?
Yeah, thank you so much for the talk. This is very interesting. I have a question which is not exactly about your simulation, but I wonder about your intuition. So if you have two black holes merging, if they have spin, they sometimes receive a kick. So the question is, imagine the same happens, but in the gas environment, will the kick be different compared to vacuum case?
I didn't mention it, but actually we studied the kick of black holes, and as far as our simulation is concerned, that is with the gas configurations that we adopted, the kick is perfectly consistent with black holes kicks in vacuum. We used the code, the post-Newtonian code by Davide Gerosa in Milan, precession code to model the kick of binaries, the same configurations that we evolved, and we found no difference between the two. Of course, it's interesting to see what kind of possible effects a kick has on the nearby environment, because that might be associated to an electromagnetic signal, and hopefully we could detect that. So it's important to accurately model it.
That's very good to know. Thank you so much.
Sure.
So I had a question about the effect of the magnetic field, actually, more than one. So the first thing is, I think you showed that when you add the magnetic field, the flow becomes monaxis symmetric rather than supporting the non-magnetized case.
I'm sorry, I don't know if it's just my problem, but I can hardly hear you. Can you please speak up a little?
Well, I think you showed that the magnetic field makes the flow more axisymmetric. Is that right? Is this correct?
Yeah.
I guess this depends
on
the configuration of the magnetic field that you choose. So what configuration were you choosing here? Is it a toroidal field or?
No, basically, you know, as I said, we consider the magnetic field to be generated from a distant secondary disk. So we just initialize the simulations with a uniform magnetic field which is aligned with the orbital angular momentum. You know, that could be the very close part of a poloidal magnetic field anchored to a subcombinary disk. And but of course, when evolving a subcombinary disk as well, we will need to seed it with a different magnetic field.
Yeah, and so that may change things again. But and the accretion rate, maybe you said it, I just overlooked it. The accretion rate changes a lot when you have the magnetic field.
Yeah, it changes not a lot, but quite. And actually, this is the same result that was found by the ARET group recently. We are still not sure about the physical interpretation because we were wondering if that could be due to the, you know, to the ISCO or to the different size of the ISCO of black holes. But we are planning to study this effect by using a particle tracing in a future suite of simulations in order to, you know, to follow more closely the evolution of the accretion flow itself.
Thanks.
Alrighty, great questions and great talk, Federico, and great talks, everybody else. I think we're out of time for this session. So let's give Federico another round of applause. Thanks for coming, everybody. I wish I could be there in person. Of course, I said that probably too many times. But have a great rest of your day, and I'll see you all later.
Thank you, Nate.
Thanks.
A great pleasure.